Can you see me? Uh, so, welcome. We're about to jump into this experiment of doing class online. So I can see a number of people appear to be uh, joining us. This is great. It's going to be an adventure. Appreciate your patience as we get this working. Um, so, a couple things. See if you can post anything in the chat. This would be a way for you to interact with me while we're talking about stuff. So there should be a little window on the right side of the screen where you can post. See if you can do that. Excellent. Great. Uh, Very cool. Very cool. One of the things that I've been worried about or thinking about with regards to class is just how are we going to create a community, um, you know, while everybody's separated, while we're not in the same place. And I think this might be a way to go about it. We can interact online, and this is great. So the chat, what I was thinking, we can use this basically during a live lecture. So, for example, I could ask you questions. Let's try that out, and then people could respond in the chat, and then I can take from that like, oh, okay, people seem to be doing okay with this, or maybe we need to spend a little more time on this subject. So let's try that. Okay. Bear with me while I'm experimenting with the whiteboard too. It's a little cumbersome. So, but we'll get up to speed here. So, for example, I could ask you all a question, like, just ah, pardon my penmanship too. I'm working on this. I got to figure out exactly how to use the pen and all this. Um, so I could ask you a question like, what is more fun to watch? And then you could reply in the chat. So we could do this during the live lecture. This is an idea that we can try. So go ahead and answer this question now. Cool, cool, cool. This is great. So one of the things I was curious about was basically how big the delay is between all of us, and it looks like it's pretty quick. Like it's, I don't know, 10 seconds or so, and people can plug in. So this is fantastic. Okay, so of course we'll use this for, physics questions, but this is a way that would allow us to interact in more or less real time. Super. Okay. So, sort of another thing, kind of along the same lines, I was thinking was while we're talking about material, um, I could ask a question like, is this topic confusing, etc. And people could respond in the chat with, say, a thumbs up or a thumbs down. So why don't we try that? Oops. So go ahead and reply. Just see how quick that works as well. And I appreciate your patience as we kind of just feel out the system and get make sure everything is working. This looks like it could work. So we could go through a topic And then if there are lots of questions, or not questions or whatever, I can get some feedback from you, and we can use that to kind of steer how things go. So I am very encouraged that this will work, that we'll be able to work this. It's cool to see the emojis come through. I'm really happy if we can kind of take this system that we often use for, like listening to music or watching videos about how to fix something or something like that and apply it to class. I think that would be pretty neat. Okay. So that's the chat, what I was sort of thinking. And then if folks have questions, like bigger questions, you can post a comment. Are people able to see the comments, or are you able to do that? So you could go ahead and post now if you want. If that's not working, I'll figure out how to fix that. Great. Okay, let me... super. Okay. So appreciate your patience. We'll have to experiment with this as we go, but let's start talking about some actual physics. So a week ago, before class was interrupted and everything, we had just started. We were in our first week. We'd had a few lectures, and we had basically talked about kinematics, i.e., we had talked about describing motion with math. And now, we are transitioning from one dimension into two dimensions. And so we're moving from chapter 2 to chapter 3. So, oops. So, and chapter 3 talks about things in more than one dimension. So 2D kinematics. And in order to be able to look at problems in two dimensions, one of the things that we need to talk about is vectors. So we're going to do a little bit of a vector review. Since our vector review got canceled because we're not meeting in person, we'll talk a little bit about that now. So, let me look at my notes here. Vectors. As opposed to scalars, vectors have both a size and a direction. So, they have a size and a direction. So one thing that we can do is we can look at vectors graphically, and the simplest situation is oh shoot, whoops, is to consider, for example, you have a vector that's pointed this way, and maybe we have another vector that's pointed this way, and we could label these. You could see that if you wanted to add these together, you would get something that's just the same direction, but the length of both of them combined. Okay. So that's kind of the simplest situation because that's still basically in one dimension. And you could imagine, well, what happens if you change the sign of one of these? So if A is still like this, B is still like this, but now we do A minus B. What that would look like is you can put one like this, and then now the other one would be like this, and you would get something, if this is equal to this. In this situation, it'd be basically equal to not anything, like they would cancel out if they were the same exact length. Okay. So that's the simplest situation, but really where we want to go is more dimensions. So consider now, if you have something going to start to include a coordinate system. Suppose we had now A is along the x-axis and B is along the y-axis. Okay. If we wanted to add these together, you can do this sort of thing graphically. So and what you would do is you would connect from head to tail for each of these vectors. And so the result would be a vector like this. Okay. So you can see, just looking at my cartoon of this, how it quickly gets very difficult to do this in a quantitative way. You can get kind of an idea of how to do things, but if you wanted the actual length of this resultant vector and the exact angle to be accurate based on doing this with a graphical, like drawing a picture, it's very difficult. So I'll put that as a note. Oops, sorry. So what we do instead is we need to be able to break our vectors into components and add the components, for example, or manipulate the components. And this will be something that we use in chapter 3 for talking about projectile motion. But this is also going to be critically important. We're going to use it when we're talking about Newton's laws and looking at the sum of forces. It's a really essential skill that you'll need in order to solve problems using Newton's laws. So we're going to use this now, and you're going to use it later, and it's really something that you have to be solid on. And it's kind of the bread and butter of a lot of tasks that you would need to do, especially in an area like mechanical engineering. In other words, engineers need to be able to manipulate vectors and do operations with vectors. Okay. Questions? Is this okay so far? Maybe we could get a thumbs up in the chat, and I'll take a glance at that. Can everybody hear me? Is everything good? Give me a thumbs up, and then we'll proceed. Okay. Awesome. Excellent. Okay. So I'm going to clear this. I may try and figure out some ways to post the whiteboards, but the whiteboard in Windows is not super flexible, but we can refer back to the video. The video will definitely be posted. So I'm going to clear this. Okay. So if we want to be more quantitative, one of the things that we need to be able to do is break a vector into components. So this is sort of an essential skill, like I was mentioning. Okay. So sort of the quintessential example of this is you have a vector. It's often drawn along the x-axis. You have an angle theta. So this is the total vector. I'll just call it v for this. and we have our x and y axis here. So, and we're working in 2 dimensions. You can imagine generalizing this to 3 dimensions. Hopefully we'll do that in one of the lab activities. But we want to relate, for example, the piece of this vector that's along the x-axis and the piece of this vector that's along the y-axis. And you do that by using your trig functions. This is the short story. So I'm going to go through this in maybe more detail than you want the first time. And then as we proceed, we'll use this. We're going to kind of assume that you're up to speed, that you're getting fluent with it. And then you'll be responsible for using it, in problems. And but we'll go in kind of all the gory details just to begin. Shoot. So the trig functions that we have that relate the x and the y pieces. Many or most of you probably know this already, but for example, sine theta is the ratio of the opposite side over the hypotenuse. Oops. Okay. So that's Vy over V. And I didn't put the little vector sign over that because in this situation, we're talking about just the magnitude. Okay. And so if you wanted Vy, what you're really doing is multiplying this V across. And so Vy, oh sweet, I can erase, is V sine theta. Okay. Similarly, cosine theta is Vx over V. So if you want Vx, Vx is just V cosine, oops. Sorry, bear with me. I'll get better with the pen and all that. Okay, is V cosine theta. Now, I want to be very careful about this and emphasize to you that this is for this picture, okay? And this is probably the situation that you're most familiar with. But let me, I can put it in a different color. Caution. This depends on the context. So what I mean is, this is right for this picture, and this is probably what's most familiar for you. But if I was to do this differently, so this looks the same, right? But now, suppose you encounter a question where, I'll do this in a different color. Theta is specified off the y-axis. In this situation, so here's our total V. Our Vx and our Vy components are going to be not sine and cosine theta, respectively. But now you would have to see, okay, so Vx, if we want that, we want the opposite over the hypotenuse. So in this situation, Vx is going to be V sine theta. Okay. Actually, let me be more clear about this. I'm going to put this not as theta. I'll use a different symbol for this angle. Let's use alpha, just so they're distinct. But in this case, you can see that Vx would be V sine alpha, and Vy is going to be V cosine, alpha. Okay. Okay, let me see. So we're getting some good questions. Yeah, so there's a number of questions about if this will be in degrees or radians. So it kind of depends on the context. A lot of times angles seem to be specified in the book and in homework problems in degrees. And that would be an issue if you go to evaluate a trig function, because if you use a trig function that's expecting radians, an angle in radians, and you give it an angle in degrees, you'll get you won't get what you want, or vice versa. So we can, I'll put another, another caution note here. Ah, sorry. So that's a good point. That's a good question. Thanks for asking about that. You're going to have to, yeah, be mindful of that. Are there questions about this this argument that I've made, being careful about context? Basically, I just don't want you to rely on these definitions. Let's see here. Can I don't want you to be assume that this is always the case, that Vy is V sine theta or Vx is V cosine theta. But make sure and refer to your picture, refer to your diagram. This can help you straighten out which is which and make sure you have the component that you want. So yeah, any questions on that? Good. Maybe give me a thumbs up if that's good, and we'll keep on keeping on here. Or if you have questions, shoot me a question. Okay. Okay, this is good. Sounds like we're kind of on the same page. If there's a lingering question, put it in the comments, and we'll come back. I'll look at those after the stream, and we can get a sense if there's anything, and we can revisit it. Okay, excellent. So one thing that I want to, a detail that I want to look at next is something called unit vectors. So I suspect people have been exposed to this, but it's kind of weird, so we'll take a second to talk about that. Okay, so this, I mean, we'll do more stuff with vectors. This is just, I want to give you kind of the bare minimum so that you can get started, and then we'll add stuff as we go. So looking at your math surveys, many are in Calc 2, Calc 3. Like, we're going to talk eventually about the dot product with regards to work. We'll be talking about the cross product. Oh, I see a question. Will the notes be posted? So I have to figure out how to export stuff from the whiteboard. For now, at least initially, the stream will be posted, and I'll see what I can do about exporting the notes themselves. Okay, so yeah, like I said, we'll add more vector operations, vector math operations to our toolbox. We'll kind of give you the minimum that you need to get started now, and then go from there. So unit vectors, this is one other kind of critical topic because there are sort of some different conventions. So unit vectors are special vectors. They're vectors of length 1. That point along the axes of our coordinate system. So, and part of why I bring this up is because there are different conventions for this. And the convention, it doesn't, I mean, it means the same thing, but we want to be consistent. So the convention that we use is I, J, K. So have you guys seen this before? Maybe put a yes or no uh, in the chat, and I'll take a look at that. So, and what this means is if you have your coordinate system in 3 dimensions, the I hat points along the x-axis, j hat points along the y-axis, and k hat points along the z-axis. Okay. So it's kind of a mix. Had it in Calc 3, no, yes, some no's and yeses. That's okay. That's totally fine. If you haven't seen this before, it's totally fine if you haven't seen it. We'll use it. You'll get comfortable with it. There are other conventions. Sometimes folks use x hat, j hat, and k hat. We're using I, j, x hat, x hat, y hat, and z hat. Sorry, excuse me. We're using I hat, j hat, and k hat. And they have a length of 1, and they point along the axes of our coordinate system. So for example, you can express a vector in terms of this. If you have a vector that's, say, pointing along the x-axis, like we had before, let's say that this thing has a length of 4. If we wanted to write this as a vector to indicate that direction information, this would be 4 I hat. Okay, so you can imagine this gets more complicated when you have a vector that's pointing along an angle, at an angle, but you can break it into components, i.e. you can break it into the piece along x and the piece along y. Okay, so great. Like I said, it's okay if you haven't seen this before. We will, me making use of this, you'll get comfortable with it. Okay. Good. So let's move on to projectile motion. So this is all this discussion, all I've told you about vectors has been preparation to give you some of the context that you need to look at problems in 2 dimensions. So, and this is kind of a fun topic. Oops, sorry. Projectile motion. So, and this is basically section 3.7 in your book. And you know, it occurs to me, one of the things that's going to be, you know, maybe even more important now that we're all at a distance, that we're not able to work together in the same place, is looking at your textbook. I'm going to follow your textbook closely because I think that'll help to kind of keep everything kind of all the same. But reading the textbook will be a great help because since it's more difficult for us to communicate, be sure to read your book. Projectile motion. So this is fun because there's all these different kinds of problems that we can look at. You know, you can look at, just to give you some examples, you can solve different kinds of problems like, suppose you shoot something projectile at an angle. I mean, this is sort of the most basic problem, is basically you want to know where it lands. But this, oops, shoot. This is the same math as problems like what if you you throw something off of a building or you drop it off of a building. Oh no, my eraser isn't working. Okay. Or you could throw it up and you want to know where it goes. So these are all variations on projectile motion. It's all kind of the same stuff. Okay, so and kind of the general strategy for this is you're going to need to break oops. Break the velocity, initial velocity, sorry, into x and y components. And then the y component, actually, let me say it this way. The analysis in the y direction gives you the time. So this is just like free fall. It's the same thing as free fall. That same math that we've looked at in one dimension allows you to find the time. And then the x analysis with that time. So basically the x in the x direction, the time from here times the velocity in the x direction gives you the range, gives you the distance in x. So that's the deal. You break it into components, you look at the y analysis to find the time, and then you look at the x direction to find the range. Okay. Okay. Any questions so far? Okay. Let's take a second to see. Yeah, see some questions about internet. Hopefully when it posts, it'll be easier to watch, or you can, and yes, so that's a critical critical realization. The time is the same for x and y. So if you find the time that it takes to fall, that's the same time that it'll be traveling in the x direction. You can write that on here. The time is the same for x and y. Okay, let's see. It's 3 again. Yeah, so basically for part 3, the x is going to be the time that you found from here, from part 2, from step 2, times the velocity in the x direction. I will give you an example that shows this in a little more detail. So let me just emphasize this. Okay. So is it possible to work to solve the x direction time first and then use that time to solve for the y direction? Absolutely. So you can imagine kind of where this is going. There's all different kinds of problems. You might be given a problem where it says, hey, it went this far. how high up was it? Or what angle did you throw it at? So we'll look at some examples to start to give you a flavor for this. Or I'll break this into a little more detail. So let me show you. Let me clear the board here. Okay. So, oops. Let's look at our kind of prototypical example first. You have some projectile that's launched at an angle theta, and sorry. Gotta figure out how to not do that. And kind of the simplest case would be, hey, we want to know where does this thing land? X direction, Y direction. Okay, so we need to break this velocity into components in the X and Y direction. So just like we had talked about with vectors generally, this is our angle is given in the same way. So for this, V naught Y is V naught sine theta. Okay. So if we want to find the time, we can use our one-dimensional expression that features time, basically that we used for free fall. We're going to find it from Y is going to be Y naught plus V naught YT plus 1/2 AT squared. But really, this is minus 1/2 GT squared, right? Because we're falling. The object is falling. It's moving sideways, but it's always falling as well. So notice, if we draw our coordinate system so that the origin of the coordinate system is where it starts from, the object is going to start at y initial equals 0. And once it lands back on the ground, y final will also be 0. Okay, and then we have v naught y right here. So we can put that in and solve for time. And this should look pretty familiar to what we were doing before. Notice there's a factor of t that's in both of these, but I'll leave it in for now, or how about I factor it out and then you can see. So this will be a factor of t times v naught sine theta minus 1/2 gt. Okay. So one solution for this is t equals 0. Okay. And then the other solution for the time would be, where does this argument equal 0? So for that, we could solve this. We would have negative v naught sine theta equals negative gt. And then we could solve this for t. So we would multiply by negative 2. I'll just write it out. We would have 2 v naught sine theta over g. Okay. So that's our other time. Okay. So that's the time. And then if we want to find how far it goes, i.e., so this is the little mini outline I gave you. This is step 2. Step 3, we need to recognize that x is going to be v naught x times time. Okay. So, I neglected to put in our v naught x. So what is v naught x? V naught cosine theta. Okay. Somebody caught a mistake. Yes, this would be t squared. Okay. So this is sort of the simple case for landing, being launched and landing at the same elevation. But our x will be v naught x times time. We have the time from here. We have v naught x here. So we can get an expression for the range x that depends on v naught and it depends on theta. And that total expression would be those two, the time and v naught x multiplied together. So it would be v naught cosine theta times 2 v naught sine theta over g. Okay. Let's see. Oh, snap. I got this. Yeah. You're right. My mistake. Okay. All right. Let me see here. Okay. Good. So this would be a general expression, and we can simplify this a little bit. Notice this will be 2 v naught squared sine theta times cosine theta over g. You can also make use, there's a trig identity. You can rewrite this. If you use the trig identity, that sine theta, wait a second. Sine, well, here, let me write this up here. So it so happens that sine 2 theta is 2 sine theta cosine theta. So you can put that in here as well and consolidate this down to one trig function. So this also equals, in other words, v naught squared over g times sine of 2 theta. Okay. So this is a general expression for the simple case where things are launched from and land at the same elevation. And this tells you how it depends on v naught, the initial velocity, and how it depends on theta. So, okay. A couple things to note. Notice that it depends on v naught squared. So let's see. It's proportional to v naught squared. Which means if you were to double the initial velocity, you pick up 4 times the range, which is kind of interesting. So is this a general equation? Sort of. I mean, this is one case. You can imagine, I'll show you how it gets more complicated, but this one is used in some problems, and they derive it in your textbook as sort of a range equation. Let's see. Do we have to use the trig identities? I'm not sure what you mean. Yeah, you don't. Oh yeah, you don't have to use that trig identity. The other thing that I wanted to note about this, so it's proportional to v naught squared. The other thing that's of interest is that where is the maximum value for this? So if you look at it's probably easier to see in this version where we've put it in terms of sine of 2 theta. But for what angle would this sine of 2 theta be maximized? Let's try putting in the chat. What angle would give this expression its maximum value? I'll put that over here for, well, let's see. Yeah, okay. Everybody's on the same page. Good. You can see since sine of 2 theta is going to be maximum when 2 theta, the argument, is 90 degrees. That means that the angle that's going to give you the maximum range is theta equals 45 degrees. So we'll put that down here as a note equal as well. Okay. Okay. Good. It sounds like folks are okay with that. Any questions? Okay. Good. Maybe give me a thumbs up and we'll proceed. Let's look at an example question next, I think. Second equation. So the second equation, the equation just in terms of one trig function, it's just a way to reorganize it. It's not essential to use that or anything. You can use, you can do it in different ways. In practice, you're not necessarily going to use this exact equation a lot. It's just, it gives us an excuse to kind of walk through the steps with a problem, or to lay out the logic for solving these kinds of problems. Okay, it looks like people are doing okay. I am going to clear the board and let's look at an example question. Okay, so let me see if I can do this here. Oh wow, that's really small. I'm trying to come up with ways to do this efficiently. So here's let me make this bigger. I can paste text in here and then you don't have to suffer through my handwriting. So this is a question out of your textbook, and let's work through this one to give you a sense of how you kind of approach these problems. So a ball is thrown horizontally from the roof of a building 9 meters tall and lands 9.5 meters from the base. What's the ball's initial speed? Okay. So first thing that I would recommend with something like this is give yourself a little picture. Give yourself a picture. Okay. So one thing to notice with this is it says horizontally. That's a clue that's telling us that the initial velocity is exclusively in the x direction. So our picture should incorporate a coordinate. Let me draw this differently. Let me put the coordinate system in a different color. Come on, U. So we're going to have our coordinate system, the origin of our coordinate system, at the base of the building. And we know that the ball is thrown initially at velocity of, or that's what we're looking for, rather. But we do know that it's in the x direction, and in terms of our unit vectors, that's the I hat direction. We also know that this building is 9 meters tall. And we know that the thing lands 9.5 meters from the base. Okay, so we want to know what is that initial speed. So we can follow this same kind of prescription. From the y direction, we can get the time. Okay, so let's just write out our general thing and then comment on it. We know that y is going to be y naught plus v naught t minus 1/2 gt squared. Now, since we're throwing it horizontally, the v naught, and really this should be v naught y, v naught y, we know is going to be 0. In other words, it's dropped in the y direction. There's no velocity component in the y, initial velocity component in the y direction. The other thing that we know looking at this is the fact that the final position in y, the final height is going to be 0 according to our coordinate system because the origin of the coordinate system is at the ground. So then what we can do is, we know both of those things are 0. We can solve this for t, i.e. solve this for the time. So we would subtract our y naught. We would multiply by -2, divide by g, and take a square root. Okay. And that would give us the time. Okay. And then the other thing that we have is sort of our next. So this was in our previous, in the previous stuff. These were sort of steps 2, and then steps 3 was to find the range. So the range, like I said, is v naught t. Let me be more precise. V naught x times t. In this case, since the velocity is all along x, I could put that, I'll add an annotation over here that v naught x equals v naught because it's only in the x direction because it was thrown horizontally. Okay, so then we have an expression for t from here. We know how far it went. We could solve this for v naught. So in other words, v naught x, or v naught, is going to equal x over t. So that is going to be the x that we have divided by t. So we can put in our numbers now. Meters divided by, so this will be 2 times y naught times 9 over 9.8. Okay. And so we have a question. This is assuming acceleration is constant. Yep. So this stuff builds on what we were doing in chapter 2 for conditions of constant acceleration. So g is constant for our purposes. We'll talk about in chapter 6 how this depends on, really it depends on how far you're falling. So if you start talking about satellites and stuff that are significant distances away, it's different, but for our purposes in this situation, g is constant, so acceleration is constant. So yeah, so if you punch the numbers, can anybody, how do you guys punch numbers on your computer? You can try evaluating this on your computer, and I can show you some ways to do that on Wednesday as well. But for this simple problem, this would give you, or you can see if you get the same thing as me. I get that this is 7 meters per second. And then if we're being careful, this will be in the I hat direction. It's in the x direction. Okay, so this is an example, simple problem. So this is kind of the starting point because we didn't have anything at an angle. Okay, good. So it looks like some folks are getting the same thing. So this is sort of the simplest, or a simple example. You can see, and what we'll look at next time is, so where this is going, you can see if you throw it at an angle, for example, then v naught y is not equal to 0. And in that case, you would have y plus v naught y t minus 1/2 gt squared. In other words, you would have a quadratic. So we'll talk about that next time, and I can show you some techniques for solving that. So is the official terminology I hat? Yeah. Yep, I hat. This little thing on top of the vector, so we can, if I like draw this big, this indicates unit vector, as opposed to, like, you might have something like this. This indicates that this is a vector. So these are things to help us keep track. So that's kind of our simplest problem. So this is a good question. Would you like us to direct? So that's what I was going to present today, but you can stick around for a little while. We can try and talk logistics here. So maybe before we do that, are there any questions on this this issue in particular, this problem? Are folks okay with that? We'll do more practice with this sort of thing and look at more complicated problems on Wednesday. Okay, yeah, it looks like people are okay at this point. So we'll look at more, like I said, we'll look at more complicated problems. And I think we'll look at this on the computer as well, because this is one that, since we were going to do a lab on projectile motion, and in lieu of that, we're going to look at something on the computer. So if you yeah, so with regards to homework on this stuff, there are a couple homework problems that involve projectile motion. So that's the stuff in chapter 3. So of the first assignment, something like 2 of the problems, 3 of the problems were in chapter 3. Let's see. So we'll have a chance to talk more about that on Wednesday. If folks have any questions about the homework, we can discuss that on Wednesday as well, and I can speak to that. And then the new homework assignment we'll post on Wednesday evening. Okay. So there's a good question here. Would you like us to direct most of our questions we have after the lecture about homework or lab to Microsoft Teams, or do you have a different method? Yeah, that's a good question. I'm not sure. The Teams, we could try Teams. One, I would think, so how about this? For stuff that's related to about lecture, let's try posting in the comments, and I can look at that. That way we would kind of be looking at the same thing, and I can respond to it there, or we can respond to it there, because other people can see the comments as well. And then for lab, let's try lab in Microsoft Teams. We're going to try that tomorrow. I think it's going to be, I don't have any sense of how well that's going to work. They've been encouraging us to use that, but I don't know. So let's do lecture in the comments, and then lab we can talk about in the Teams. And I'll have some more stuff prepared for you for lab tomorrow. I'll send you some stuff later today, or something that I'm working up. So let me actually let me clear this. And I'll just put a couple reminders, notes here. So let's do, sorry. So I'll post this to, I'll post this to the playlist. You'll notice the video, if you've clicked on that link so far, there was a little, I had an intro video, and then also there's some videos from another professor at MIT that's like, kind of a grandfatherly, wizardly professor who has a lot of cool demonstrations and stuff. Those lectures aren't mandatory or anything, but it's some additional really cool context. So I figure one of the things that we can make use of with the YouTube playlist is we can fold in other material from other sources. So I think that'll be nice. In terms of the lecture questions, let's look at those in the comments, and I can reply to that. Lab questions, let's look at teams. So also, we can make a lab questions discussion channel on Blackboard. So since I don't really know how well Teams is going to go, I'll create this after lecture. With regards to the freefall lab, some folks have submitted those already, and that's great. If you're still working on it, that's totally fine. We'll talk about it. We can address questions about that in during the lab time. So this week is fine for freefall. That has gotten all messed up for everybody because only half the sections had lab. So a number of students have asked me questions about that, and it's hard to address. Okay, so Teams is preferred over Blackboard. Yeah, so one of the things I would be looking for from you guys actually, just in terms of logistics, is if you find that professors are using Teams in your other classes, how well is it working? Are there features that you can point us to that will help us? Yeah, so Teams is great. Maybe Teams will work well. That's definitely an option. I'll see if I can come up with how to make like a channel in there then for some of these subjects. I could see how it's pretty easy to do it in Blackboard. You could have, Teams is all right. So Teams sounds like people are okay with Teams. I see. You can get notifications. Okay. This is good. I think basically we're going to have to see how it goes and kind of adjust from there. I'm stoked. It seemed like the lecture via YouTube worked okay. One of the things is too that this should post. I see. Oh, with regards to last week's homework won't be due until this coming Wednesday. It's been extended by a week. Yeah, sorry if there's confusion about that. And then with regards, one other thing. There was a homework, somebody pointed out to me, like a homework assignment had posted that was in error. It was like the previous version of the homework assignment for this week. That was a mistake. I took that down. So yeah, where it says, is homework 2 due today? No. You don't have another homework assignment until this coming Wednesday. So you're not going to have more than one homework assignment at a time. So yeah, sorry, that was a mistake. That was my fault. I got screwed up with having the week gap in there. Okay. Well, that's about all I wanted to get across, but I'll stick around for a bit as folks have questions, we can talk about it. I can respond to them here. Yeah, personal emails. I've gotten a number of questions about lab. I'll try and get back to you on lab today or during lab. Lab has definitely been kind of thrown into disarray. Sorry for not getting back to you quicker about those issues. Other questions? Yeah. No, it's been I've been distracted just trying to make sure that things would work. So the lab has kind of been put on the back burner, but I'll be in contact with folks about that. Yeah, my mistake. So with regards to homework, homework will be due on Wednesday. So yeah, generally homework will be posted and due on Wednesday, and you'll have a week to do it. So do all students view the lab tomorrow, even if they have regular scheduled lab on Friday? So we're going to have lab sections separate. We'll do a smaller group. We're not going to do it on YouTube. We'll try and do it in teams. Yeah, and then ideally labs would be due, but I have to be honest with you, like the labs are kind of scrambled because there's a lot of stuff that we're not going to be able to do or we're going to have to kind of adjust. So I would say the main thing for lab at this point. Yeah, so a number of questions. These are excellent questions. The main thing for lab, I would say, is if you haven't already, uh, try and install MATLAB. I think this will let us do some simulations and some other stuff that will be good. Will let us work on some good skills, even if we can't do some of the experiments in person. So, and then, yeah, I'm not sure if you can answer this question, but you think we'll actually go back to school in April, and how will exams work? So those are excellent big picture questions that I'm not sure about the answers to be honest. Uh, I haven't heard anything back, or I mean, I haven't heard anything additionally from administration or anything about uh, them not having school resume in April, but I think basically everybody is waiting and seeing, how do things go the next couple weeks, and then they're going to make a decision based on that. I think some institutions have called it for the rest of the quarter, but I don't know. And then how will exams work? That's another area that's just not well suited to doing online, unfortunately. I put some information in the intro video for online about that. We have some ideas. We may be able to do an exam, like a quiz problem through the homework system, but that's something that I'm working on right now. Let's see. So for those that did not have the first lab, I posted some data and I posted a link to a YouTube video that shows basically what the lab is. And we'll address that during lab time in teams as well. But yeah, you can do the best that you can working through it on your own. Uh, basically, just because uh, I don't want it to be that the first that you don't have anything, but I understand that since we didn't have time to work together, I'm not gonna like really punish you for not being able to do as much on that as the group who actually had lab. So just kind of do the best you can. Upload your stuff to the assignment in Blackboard, and then I will give you some feedback. But don't think of it as don't worry about like getting graded negatively about it. I'm basically just gonna grade for like, hey, you submitted stuff and you've yeah, we'll talk about it in during lab in Teams as well. Yeah, no, I totally feel you. I am totally taking that into account. The first lab was kind of hard to do without doing the lab. I agree. I'm, yeah. And then I've gotten some questions from students on labs. I'll reply to you on that stuff today. These are excellent questions. I really appreciate the feedback. This helps me nail down, kind of focus on how we're going to proceed from here. I think if we can keep communication open and figure out like, okay, we adjust this, we dial this in, this isn't working, we do this instead, that'll be really, really helpful for us to make progress as a group. Um, so I really appreciate your participation today. I'm uh, really glad that this seemed to work. So we'll jump into the other aspects of class as well and try and make sure those things work and proceed from there. Other questions? Well, if there are other questions, we can shoot me an email or maybe Teams. Maybe we should start using Teams. Um, I'll try working on that as well. Uh, and then otherwise, we'll do the best that we can. So I hope you all are safe and that your families are well and everything. And it's definitely a wild thing to have school just sort of uh, well, everything sort of disrupted like this. So I'll do what I can to make sure that we learn together. I'm learning tons from this, so it's interesting. It's quite a thing, and yeah, I'm gonna sign off, but I will be in communication with you, and we'll talk to some of you tomorrow during your normal lab time in Teams. Okay.